Okay, now we are going to investigate the pointwise convergence domain. I mean this series is defined where, or equivalently where this series is convergent for which x. So for example, if x's are less than 1, I mean the magnitude of x, of course it cannot be -1, because if x is -1, this becomes -1 to the power n. So sometimes it is becoming 0, so it is undefined, so we don't allow x to be -1. If x is the magnitude of x is less than 1, we have a divergent series, right? Because then limit n goes to infinity, 1 plus x to the power n becomes 1 over 1 plus 0. So it is 1 and not 0. So by n-term test, it is divergent. Test, it's divergent. Now, if it is bigger than 1, if the magnitude of x is bigger than 1, then since it is bigger than 1, if you take some powers of n, some powers of x, it exceeds 2, for example. I need 2, that's why I'm talking about 2. Why? Because since it is bigger than 1, the limit of x to the power n becomes unbounded and infinity. That's why for sufficient large n's, we have x to the power n is bigger than 2. You will understand why I'm talking about 2, because then I can say that 1 over x to the power n is less than 2 over x to the power n. How can we show it? Because since make this cross multiplication, you will end up with x and less than 2x to the power n minus 2. But it is true, right? Because and since x to the power n is bigger than 2, right? When you put this -2 to the other side and x to the power n to the other this side, you will end up with x to the power n and 2 here. So you get this. So that's why it is correct. And we have then 1 over 1 plus x to the power n in absolute value is less than 1 over x to the power n minus 1. Why it is correct? Because your values are bigger than 1, right? So this part is bigger than 1, but you are subtracting some numbers, so this part is still positive, but it is less than this part. So if your denominator is less, this is correct, and by this above we have this 2 over x to the power n. But the series of this general term is then convergent. 2 over x to the power n is convergent. This is a geometric series. And so by comparison test, direct comparison test, the original series, I mean this one, is convergent. So my pointwise convergence is true for x is bigger than 1, strictly bigger than 1. or if you want to have some interval, it is equivalent to r minus minus 1 1. Okay, this is the interval of convergence, but since we are taking the absolute value, it is even absolute convergence. Okay, again we have some cases. I want to simplify this general term, but in order to do that, x shouldn't be 0. So first let us understand when x is 0. If x is 0, then what do I have? I have zeros, so the series is just 0, which is 0, so convergent. If not, then the series become 1 plus x to the power n. Let me cancel x to the power n, or divide each side above and below, or denominator by x to the power n. Since it is not 0, I can do that. So we have 1 over 1 plus 1 over x to the power n. So in this case, it is very similar to the part A that we have dealt with in the previous slide. So, okay, let me do it in this way. So this is equal to infinity 1 plus x to the power minus n. Oh, okay. So we have x is less than 1. Okay, I need to remind you the previous video. Is convergent when x is bigger than 1. So in this case, since we are inverting the power of x, you need to change the interval. So this is convergent, pointwise convergent when x is, less than 1. Okay, and let me add this information about part A by part A. Okay, so let us show the uniform convergence of the following series. First of all, we can simplify this inside because we have some because I have seen this pi over 2 and some arctangent. Immediately I have the following thing: pi over 2 is equal to arctangent x plus arctangent 1 over x. Arctangent 1 over x. Of course, x is bigger than 0. We can also prove it. Let us draw a right triangle. Okay. Call this theta. Okay, let me call theta is arctangent x. Now my tangent theta is then x. It means that it is x over 1. Right. So what is then arctangent 1 over x? So let me also call this another angle. Let me call it beta. Beta. And beta is arctangent 1 over x. Right? Because then tangent beta is 1 over x. Tangent beta is 1 over x. So these are true. But as you can see, since the summation of the angles in the triangle is 180 degrees or pi, alpha plus beta is pi over 2. And by definition, of course, theta is arctangent x and beta is arctangent 1 over x. So this holds for positive angles. Now I'm gonna use this equality here. So we have this series. Let me just copy and paste here. This is equal to summation infinity n equals to 1. So if you take arctangent x over there, you will have pi over 2 minus arctangent blah blah is arctangent 1 over blah blah. So this is just arctangent 1 over n square 1 plus x square. Okay. Now we can also consider arctangent 1 over n square 1 plus x square less than the inside, because you can also use the Taylor expansion. The arctangent x is less than x. That's why I can do the following: 1 over n square 1 plus x square. So that's because arctangent x is less than x. Of course, I'm talking about positive numbers, so let me put. Okay, then obviously x square is always positive or 0, but this is bigger or equal to 1. So I can do the following: this whole thing is less than 1 over n square. So as you can see, 1 over n square is divergent, but I'm gonna use m test, so I'm defining this to be m n, and series of mn's are convergent by p test, because this is bigger than 1, so this series is convergent. And since this is also positive, right, because inside is always positive, so by m term test, no, not m term, m test, the whole series is then convergent. So by Weierstrass m test, it is convergent. It is uniformly convergent. Okay, now for look at this series, I will use this following thing: ln 1 plus x is less than x. Okay, now instead of x, if you plug nx, what do you get? You get the following inequalities: ln 1 plus nx over nx to the power n. Using this inequality, I have nx over nx to the power n. It is equal to 1 over x to the power n minus 1. And as you can see, since x is starting, okay, the domain is from 2 to infinity. So this x is always bigger than 2, right? Okay, so let me do it. 1 over 2 to the power n minus 1. Because of this, x is always bigger than or equal to 2. If you flip this, 1 over x is less than 1 over 2. If you take the corresponding powers, so you get this inequality. Maybe you can also put equality. As you can see, let me define this to be mn, and this 2 to the power n minus 1 is geometric series, and 1 over 2 is less than 1, so convergence. So by Weierstrass m test, the series is convergent. Okay, let us given this series and check that uniform convergent or not. So since it's a bit messy, I cannot see a direct candidate for m test, But I can always calculate the supremum of it, right? So let us calculate the supremum of if it is called f of n of x, f of n x, x in a, I mean real numbers. So since it is messy, I need to calculate the derivative of it to calculate the critical points. So let me take the derivative with respect to x of f of n x. So you will get, okay, n square, so it is independent of the variable, so you can just take it out, x square, so 2x e to the power minus n square x plus x square, the derivative of e n square x, or let me just put it like that, n square d over dx of the absolute value of x. But as you can see, since absolute value is not differentiable at the origin, but I can still calculate the derivative elsewhere as the following: 1 if x is positive and minus 1 if x is negative. So first let me simplify this derivation. I can take the common parentheses more. Of course it is not correct because I have the term n to the power a to the power minus n squared x. So let me take the common parenthesis of x and this thing, x e to the power minus n squared x. So we have 2 minus n squared x and d over dx and absolute value of x. Okay, since I'm calculating the critical points, finding critical points, let us analyze when this thing is 0. First, this term is 0 if and only if x is 0, right? Because this never is 0, this never is 0, because n is starting from 1. So only thing that can make this part 0 is 0. Okay, so I get 1 critical point. And by the way, this is not even critical, this is singular point, because this x equals 0 makes this derivative undefined. So I mean this is undefined at x equals 0, so it is singular point. But by the definition of critical points, it's still critical points. So, and we have another critical points that can come from this part. Okay, when x is not 0, this can be 0. When, okay, I can calculate this: 2 minus n square x d over dx is 0. But first, concentrate on positive values. When x's are positive, this thing is 1. So I have x is equal to 2 over n square. Yep. If x is negative, x is minus 2 over n square. Now let me, okay, I have 3 critical points, right? So let me just plug them in. 0. It gives me 0, right? If you put x equals 0. If you put 2 over n square, you will get n square 4 over n to the power 4 e to the power minus n square 2 over n square. By the way, you will see that since this is absolute value of x and here you are taking the square, this and this will give the same value. So this is indeed the minus 2 over n square. And if you simplify it, this is equal to 4 over n to the power 2 e to the power 2. Okay. So this is my supremum, right? So since it is positive, it will come out of this absolute value as this. So this is my supremum of f of n when x in real numbers. So let me make space. Okay. So then let me call this to be my Mn. So let us analyze the series of this Mn, or just call the explicit version. Is it convergent or not? How can I do it? 4 over e to the power 2 is just a constant number, so I can also see is like, since my variable is n, 4 over e to the power 2 summation infinity and 1 over n square is convergent by p-test, right? Because n square is this square is bigger than 1, so it's convergent. And by m-term test, no, not m-term test, Weierstrass m-test, my original series is then convergent. So by Weierstrass m-test, I cannot say that. The series is uniformly convergent. Okay, now look at this series. As you can see, x is independent of this value n, and you can take this out, and what is rest is just a geometric series, and we can calculate this series explicitly. Okay, let us do that. This series is then equal to x square and equals to 1 minus x square and minus 1. I can also see it as following. If you have series and starting from a, let's say, and if you have some I don't know, bn, and you can always change the indexes as following. N is equal to 0. I mean that, okay, a is positive, let me say, and natural number, of course. If you decrease by n, you need to add by a, so this means b n plus a's. So let us apply this indexing, shifting to this case to be able to calculate it. 0, so it is 1 minus x square to the power n. Now I have the following formula. X to the power n is 1 minus x if n is starting from 0. So if you apply this, you will get x square. 1 minus x square. So let us simplify. X square, you will only have 1 x square below, so it is just 1. But you can do this calculation if x is not 0, right? You cannot divide 0 by 0. But if x is 0 at the beginning, put 0, and this is 1 to the power something, but this is 0. So if I call this to be s of x, the s of x is pointwise limit. So my pointwise limit is 1 if x is not 0, 0 if x is 0. Okay, and look at my partial sums, s of n's. They are just continuous functions. Are continuous functions, right? Because you are just summing finitely many these functions at each x pointwisely, so it gives you the sequence of functions, right? But as you can see, this whole thing, x square, 1 minus x square to the power n minus 1, they are all continuous functions. If you sum them finitely many, you will also end up with a continuous function, right? Because summation of two continuous functions is again continuous. So this partial sums of the pointwise limit is continuous, but the limit is not continuous. Is not continuous. So it cannot happen, right? By some theorem, it says that if your sequence of functions are continuous, and if convergence is uniform, your convergence, if your if it is uniformly convergent, then the pointwise limit, which is equal to the uniform convergent function, should be also continuous. But in this case, it is not. So convergence and cannot be uniform.